Hello. In this video, we're going to study some triangles, some trig, and eventually some SOHCAHTOA. But before we get into all of that, let's go ahead and start with something very basic. We have a triangle here. The hypotenuse is 1. Both of these angles are 45, and we would like to determine the two missing sides. Now, to do this, we need to find some kind of method, and we might remember that when you have a right triangle, you have Pythagoras. A squared plus b squared equals c squared. And so we have c squared as 1 squared, but unfortunately having two variables means we won't be able to solve Pythagoras, at least this way. Now, let's think about this a little bit. This is 45, this is 45. Well, if both angles are the same, that makes both of these sides the same. This is actually an isosceles triangle with two sides equal. So we could call this x and this x, and so then a squared would be x, and b squared would also be x. So we would have 2x squared equals 1. Well, now we can solve this because we only have one variable. X squared equals 1 over 2. X equals the square root of 1 over 2. Square root of 1 is 1. Square root of 2 is root 2. And if we rationalize, that's going to be root 2 over 2. Okay, so each one of these is root 2 over 2. We were able to solve the triangle. That's pretty cool. And if we turned it into a decimal, just so we kind of have like an eyeball what that means as a number, this is going to be approximately 0.707. So if you're ever wondering what the decimal is, that's what we have, but it's nice to just leave it as a radical. So we were able to solve both sides of this missing triangle using Pythagoras and a little trick with the fact that it's an isosceles triangle. Let's try one that's a little more challenging. Here we have a triangle, and the bottom angle is 60. Let's determine the missing sides. Well, if this is 60 and this over here in the corner is 90, that means logically this has to be 30 because the three angles have to add up to 180. But we don't know this side down here, we don't know this side here, and clearly they're not the same, so we can't use that trick from before. I'd encourage you to pause the video and give it a try. All right, so assuming you gave it a try, the trick here is to make another copy of the triangle and place it right here. It's like imagining that this is a mirror and just mirror imaging the triangle over here. Well, if I do that, this angle will also be 30. This angle will also be 60. This side will be 1. And now, because this big triangle here, let me outline it in green. I've got this big triangle here, boom, boom, and boom. Well, the top angle here is 60. And the two corner angles are 60. So this is a 60, 60, 60. This is an equilateral triangle. Amazing. All the angles are the same, which means all the sides have to be the same. So this distance here has to be 1. But this little distance over here is simply half of that. So this has to be 1/2. All right, well, if I've done that, then I can find this missing side x back with Pythagoras. X squared plus 1/2 squared equals 1 squared. X squared equals x squared plus 1 over 4 equals 1. X squared equals 1 minus 1/4. X squared equals 3/4. And then x equals the square root of 3 over 4, which is root 3 over 2. Again, if you wanted it as a decimal, you could, just to kind of, get a handle on that number. It's approximately 0.866, but we're going to leave it as a nice radical for now. So we've been able to find these two missing sides, again, using just Pythagoras and some rules about triangles. So now let's go back to that first question. We solved it with just Pythagoras, but could we solve it with a calculator? Would there be some other method of solving it that doesn't require us to use a trick with the Pythagorean theorem or the isosceles triangle? And if you think about it, you might say to yourself, well, yeah, this is 45. This is a right angle, And I know all sorts of things about 45-degree triangles with right angles. In particular, I have my good friend SOHCAHTOA. SOHCAHTOA is a trig thing that hopefully you learned at some point in your math journeys. And it says that sine of the angle will be equal to the opposite over the hypotenuse. Cos of the angle will be equal to the adjacent over the hypotenuse. And tan of the angle will be equal to opposite over the hypotenuse. So over here we have, based on the angle 45, this is the opposite, this is the hypotenuse, and this is the adjacent. Well, if we were looking to solve for the opposite, we would probably use the hypotenuse because that's given. And so that would be the sine function. Sine of 45 degrees equals opposite over 1. Well, anything divided by 1 is just that thing, and sine 45 we can use our calculator. Now, lo and behold, if you have the Mr. Peters approved calculator, sine of 45 will give you exactly root 2 over 2. If you don't have the Mr. Peters approved calculator, unfortunately it gives you the decimal of 0.707. But assuming you're using the Casio FX 300 ES Plus, you get root 2 over 2, which is exactly the value we had earlier. This should be very shocking because we can do a question with Pythagoras, but we could also do it with SOHCAHTOA and get the same thing. This speaks to some kind of deep connection here that we want to explore. Let's try it with cos. Let's go ahead and look at the adjacent and the hypotenuse. That means we need to do cos 45 equals adjacent over hypotenuse. Hypotenuse is just 1. So that means whatever we get from cos 45 will be that adjacent side. And lo and behold, cos of 45 also gives us, you bet, root 2 over 2. So go ahead and try this question with your calculator. Again, this side over here, we'll put the 60 down here. This is 60. So this side over here will be opposite. This is adjacent. This is the hypotenuse. So use SOHCAHTOA to find the two missing sides. Go ahead and pause the video and give it a try. All right, well, you should get that sine of 60 equals opposite over 1 over, yeah, I guess I'll just put 1, yeah, over hypotenuse, which is just 1. So that means that root 3 over 2 equals the opposite, which is what we found from before. And cos of 60 equals adjacent over 1. Cos of 60 should give you 1/2. And again, that's the same we got from before. So clearly there's a connection going on here. Now let's kind of dive into this, and I want to extend our knowledge here. So I'm going to put a giant circle here, okay? These are some of the angles we've been looking at so far in the course. So we would have over here 0 degrees, 30 degrees, 45, 60, 90, and so on, right? Let's just work on that first quadrant. And if we were to work in the very first quadrant here, we could find the coordinates of this point, because this would be a little triangle, and we would have an angle of 30 over here. Well, if this is 30, this is 60, and this is basically just that triangle we had on the other page. The shorter side here has to be 1/2. The longer side has to be root 3 over 2. So that means that the x-coordinate is root 3 over 2, and the y-coordinate is 1/2. Doing the same thing for the next point, on the 45-degree triangle, both sides were root 2 over 2. So that means the x and y coordinate are root 2 over 2. At the 60, it was the other way around, so the shorter side was 1/2, and the y coordinate is root 3 over 2. Now, just to finish extending this, at 0 degrees, we don't have a triangle. The coordinates here would just be the length of the radius, and this is a circle with radius 1. So the x-coordinate would be 1 and the y-coordinate would be 0. Over at the top, the y-coordinate would now be 1 and the x-coordinate would be 0. This fills in the very first quadrant of what we're going to call the unit circle. So this is a circle with radius 1, and we can find the points at special angles, 30, 45, 60, and 90, all the way around the circle using these two special triangles that we studied. So if you look here, let's say we're going to go for the next coordinate, maybe right here. Well, this is going to be a mirror image of this coordinate. We can see that it's like the same height, so the y has to be the same. That's going to be still root 3 over 2. But now the x value is negative, so negative 1/2. And if you look, the next point mirrors over here. The next point mirrors over here. And at the very bottom, well, this is just a negative 1 on the x and a 0 on the y. So let's go back and fill this in. This would be a negative on the x, but same on the y, so negative root 2 over 2 and root 2 over 2. This would be negative root 3 over 2 and 1/2, and down at negative 1 and 0. Now these angles again, this is going to be 30 more, so 120, 135, 150, and 180, all degrees. Now we can continue this pattern of matching up angles and looking at which triangles are the same, just maybe flipping the coordinates from positive to negative or vice versa, into the bottom two quadrants. So I'll go ahead and pause the video here, give it a try, see if you can finish filling in the rest of the coordinates. All right, I'll go ahead and help you guys out here. This one is going to be that green coordinate, but now both the x and y are negative. And then over here, we also have another one of that highlighted in green. Here we have the one where they're both root 2 over 2, but now it's going to be both negative. And over here, just one of them is negative. And then finally, here we have this one again. And down at the bottom, like I mentioned, this is just 0 on the x and negative 1 on the y. All right, I'll keep filling in the angles here for you. This is 210, 225, 240, 270, all degrees, 300, 315, 330, and then of course back to 360. Okay, this should be negative root 3 over 2, negative 1/2, negative root 2 over 2, negative root 2 over 2, negative 1/2, negative root 3 over 2. Then this will be positive 1/2, root 3 over 2 is negative, positive root 2 over 2, negative root 2 over 2, and root 3 over 2, negative 1/2. All right, so we also notice that with this unit circle here, in this first quadrant, both signs are positive. In the second quadrant over here, the x is negative, the y is positive. Down here, they're both negative. And over in quadrant 4, it's positive and negative. So here we have these x and y values for our unit circle. And we're able to find them all using those special triangles. But the thing is that it's not just about finding these coordinates on this circle. It's also about using these coordinates to work back and find the sine and cos values. Let me show you what I mean. So let's say somebody asks you to find sine of 30. Well, I mean, sine of 30, that would need a calculator. But let's pretend we don't have a calculator. We would go over to our unit circle and we would find the angle of 30. Then we would say, okay, well that means we have a little triangle here, 30 degrees. And if we think about it, when we were doing our little SOHCAHTOA, sine is opposite over hypotenuse. But the hypotenuse is just 1 because it's a unit circle. So sine of 30 is equal to opposite over 1, which is just opposite. And opposite is always, in this little triangle, the y value. The y value. So sine of 30 has to equal 1/2. Now you could check this on your calculator, and if you were on the calculator section of a test or an exam, you could simply take sine of 30 and hit equals and get 1/2. But what I like about the unit circle now is two things. First off, of course, we're going to need it if we're in the no calculator section of a test or an exam, because if we're asked to find sine of 30, we won't have a calculator to punch that sine button. So we need to have the unit circle to find the value of 1/2 when we don't have our calculator. But more importantly, you might ask yourself, how does the calculator even know that the value is 1/2? Who programmed that, and how did they know sine of 30 was 1/2? And it really comes down to this unit circle and the methods we used here. This is how the values of the trig functions were first created. And so when you're using your calculator, you're really just using a shortcut of this thing. And so I like to see this and to focus on the unit circle, and we're going to study it a lot because this really underpins how sine and cos actually work on your calculator. And up until now, you've probably just been pushing the button, but it's nice to know how that button works, what it's actually doing, how it's actually coming up with those numbers. Now, we didn't add it right away on your unit circle, but I encourage you to pause the video and go back and add all of the radian measures as well. Because we don't just have degrees on that unit circle, we have radians as well. And we can use those radians to find cos of different radian values. So for example, if we were asked to find cos of 4 pi over 3, we would simply go here to 4 pi over 3. Cos is going to be the x values. So we look at that x value right there, and we get negative 1/2. Now, we can also check this on our calculator. So first we have to make sure our calculator is in radians. You click the shift button, then you click the mode button, then you click the number 4, which should say rad. Every calculator might be a little different, but this is how you do it on the Mr. Peters approved calculator. And then you know you're in radian mode because on your calculator there should be like a little R or a little rad at the top. So once you're in radian mode, you can type in cos bracket 4 pi over 3, hit equals, and you should get negative 1/2. So there we go. We've got a way to calculate trig. We can calculate cos, we can calculate sine, and we can do it all without a calculator, simply using this wonderful unit circle. Okay, so we're going to go through some examples here. I'd encourage you to pause the video and give this one a try. See if you can find sine of 405. All right, this one's a bit tricky. 405, you might be looking on that unit circle and say, well, I don't see it anywhere. Well, we have to combine our skill of coterminal angles. So we subtract the 360 from 405, and that's going to give us 45 degrees. So sine of 45 is the same as finding sine of 405. So 405 or 45, those are the same thing. Now we have to look on our unit circle for the 45. We have to look for that y value because sine is the y values, and we get root 2 over 2. Again, if you really want, you can check this on your calculator, but you have to make sure you're back to degree mode. So you have to hit shift, then you have to hit mode, then you have to hit 3. It should say deg for degree mode. And then on your calculator, you know you're in degree mode when there's a little D up at the top for degrees. If you type in sine of 405, sine of 405, you should get square root 2 over 2. All right, so let's keep on trucking. How can we find tan of 135? Just a little thing to note, tan of any angle is equal to sine of that angle over cos of that angle. This is like the definition of tan or a rule for tan. So to find tan of 135, we simply find that 135. We look at those points and we're going to use them both. Now sine is going to be the y value. So this one is going to be sine of the angle. This one is going to be cos of the angle. And so we have to stack that in a fraction. Root 2 over 2 divided by negative root 2 over 2. Now you might say this looks really tough, but it actually simplifies because we can, when dividing fractions, we can flip and multiply. So we take that second fraction here. Okay, and we're going to flip it. Then that gives us 2 root 2 over negative 2 root 2, which everything cancels, and we just get a negative 1. Okay, pause the video and try to find sine of negative 210. All right, so in this case, we have to add 360 because we have a negative angle. So negative 210 plus 360 gives us 150. So there's our nice coterminal angle. Over at 150, we're looking for sine, which means we're looking for the y value. Answer 1/2. Here's another one, cos of 8 pi over 3. Pause the video and give it a try. Okay, 8 pi over 3 is not on our unit circle because it's too big. But if I minus 2 pi, it's 8 pi over 3 minus 6 pi over 3. So that's 2 pi over 3. Oh yeah, that's right over there. And cos is going to be the x coordinate, so negative 1/2. How about tan of 1080? Pause the video, give it a try. Okay, we take that 1080, we minus a 360. Now that's not going to get us low enough. Minus another 360. That's still not going to get us low enough. Minus one more 360. That's going to give us 0 degrees. Oh, okay, so that's right over here. Tan is supposed to be sine over cos. Well, this one here is the sine. This one here is the cos. So we do 0 over 1. 0 divided by 1 is just 0. All right, and one last one, tan of 90. Pause the video and give it a try. Okay, we're at 90. This is sine. This is cos. So we get tan 90 is sine 90 over cos 90, which is 1 over 0, but we can't divide by 0. This is undefined. So the answer for this is actually undefined. And if you try it on your calculator, you should get an error when you try to do tan of 90. Math error in this case means it's undefined because we can't divide by 0. Let's go ahead and take some notes on this. So here we are learning about the unit circle. So on the unit circle, we have points, and they come from angles, right? Maybe like 60. And the point x and y is always going to give you cos of that angle and sine of that angle. So if you have the unit circle in front of you, you can use it to find cos and sine of our angle, which is, again, super useful. And it also, as a bonus, lets you find tan, because tan is just sine over cos. So again, as an example, let's find sine of 45, cos of 45, and tan of 45. Pause the video and give it a try. Okay, so based on the unit circle, you should get root 2 over 2. Oh, let me do that in another color here. So you should get root 2 over 2, root 2 over 2, and when you divide two of the same thing, you just get a 1. Now for practice, you should try worksheet 5 and 5.5. Maybe add another example or two here to your notes. And any things to remember. Probably the coolest thing to remember, I think, with the unit circle is that it really jives with the cast rule. So if you remember the cast rule, C-A-S-T, this means that cos is positive, all are positive, sine are positive, and tan is positive. And this actually relates really well because remember the two coordinates were both positive here. Then it was negative, positive. Then it was negative, negative. And then it was positive, negative. But if you look here, this is all. So positive and positive, that's because sine and cos are both positive. Over here, sine is the y value. So of course, sine is positive, y is positive. Down in the bottom right, cos is positive, so that's why x is positive, y is negative. And here only tan is positive. That's because if you took a negative divided by a negative, you get a positive, but both sine and cos on their own are both negative. So there's a nice connection there between, of course, the cast rule and the unit circle. And we're going to continue to study this as we go. I would highly recommend, for additional practice too, that you write out the unit circle. We are going to be using this a lot, and eventually you're going to be able to create the whole thing from scratch. You'll just have a blank unit circle and you'll put all the values on yourself. You don't have to draw the special triangles and do all the Pythagoras every time. We only had to do that once. But you will need to know the numbers, root 2 over 2 or root 3 over 2. Those values you'll have to know, and you'll be able to put them on the unit circle, sort of like at the beginning of a quiz or a test or an exam. That way you can use that unit circle and use those numbers to solve the questions. But again, that's coming up as we go through the next few videos. So if you don't have the whole unit circle memorized yet, don't panic. We'll spend a lot of time with it, and eventually you'll have it memorized. All right, hopefully you enjoyed this video, and as always, thanks for watching.